Morning, everybody. Do you hear me? Do you hear me? Thanks. All right, so let's talk a bit about circular motion. Few things you should know. Just 1 minute. As for translation, we always started with coordinate system. In y dimension, it means you have to say where is the origin, what are the unit. For example, this is 1, 2, and with the x-axis, you have to name it, and in square bracket, you have to say the unit. If you do it some part of this table is not sensitive, let's write here the x. So origin 1, 2, 3, 1, 2, 3, x meter. All right. So how does it look like for circular motion? Circular motion is also a one-dimensional problem. There's a central, this is the axis of the rotation. And how can we say the origin? The origin is a straight line. And you can say here, this is the theta equal 0. So this is the origin. Since we prefer radians, the unit can be like pi over 2, pi, 3 pi over 2. So these are the units. You can say this is the theta axis. And the unit is 1, since the unit is a unitless physical quantitative angle. How can I say, let's go back to translation. So if a body at x equal 2 meter, you can say this is here. The theta equal pi, you can say it's here. The only trick that after 2 pi, so this is a periodicity. So after 2 pi, physically you will have in the same position. So you are here at pi over 2, at 2 pi plus pi over 2, and at any n times 2 pi plus pi over 2, you are here at the pi over 2 position. How can we calculate with it? As usually, we had for example, theta t, let's say t squared plus 2t minus 5. With that one, you can create a tx graph. At any t, you can say, you can tell where is the body. Let's say this one. This is not that one, but similar to that. So, how can we do it for circular motion? same story. You have a theta t. Let's say it's, since the natural unit for angle is in a unit of pi, we can say it's pi over 2 t square plus, let's say, pi t plus pi over 2. I can ask, for example, where is the body at t equals 0? So since every t is 0, this is pi over 2, so we are over there on the north side of the circle. Where is the body at t equals 1? This is pi over 2 plus pi over 2. This is 2 pi. So I was here at t equals 0. And at t equals 1 second, I'm here. We have not only angular displacement but angular velocity. Angular velocity is nothing else, just derivate the angular displacement. So in this case, this is pi t plus pi. And again, we can ask, what is the angular velocity of the body at t equals 0? At t equals 0, this is pi. How fast is the pi? 1 over s. Since 1 full rotation is 2 pi, pi 1 over s means the body takes, if this is a constant, pi 1 over s takes half circle in every second. What is the period time? 2 pi over omega, 2 pi over pi. This is t. So if we have a body with the angular velocity pi, that means it takes 2 seconds to take the circle, and of course the frequency is 1 over t. This is 0.5 Hertz. Let's go further. We know the angular velocity, how it depends on time. We can calculate the angular acceleration by derivating the omega, which is pi, and its unit is 1 over s squared. So this is the kinematic circular motion. Everything is the same what we learned for translation. We just have to replace the characters. So instead of x, we use theta, instead of v, we use omega, and instead of acceleration, we use alpha. And I'm sorry, sometimes I mix it. For in Hungary we mainly use beta for angular acceleration, but in the English books it's mainly alpha, so anytime I write alpha or beta, I'm talking about the angular acceleration. What we can calculate with it? We can not only calculate the angular velocity, angular acceleration from theta t, but also can do this kind of calculation. So for example, the angular acceleration is pi over 2 1 over s squared, and I know the initial conditions. So at theta t equals 0, I'm at pi, and t equals 0, my angular velocity is pi over 4 1 over s. Means in this example I'm here at pi and move with a pi over 4 1 over s, which is a pretty slow angular velocity, but since there is angular acceleration, it will speed up. So the same way we solved the acceleration, velocity, and displacement example, we can solve it also. So for example, the omega t, the angular acceleration, is nothing else, just the omega at t equals 0, plus the integral from 0 to t, the angular acceleration, which is pi over 2, and that will be pi over 2 plus pi over 2t, and the angular displacement is the displacement at t equals 0 plus from 0 to t the angular velocity, which is, I was at the pi at t equals 0, then I moved, not equal sign but plus sign, then I moved like pi over 2t, sorry, plus pi over 4t square. Yes, and you're right. I missed it because the initial velocity was pi over 4 and we have pi over 4 here. Alright, so this is the easy example. Tomorrow we can solve some of these examples, and few things we have to learn, that the acceleration is the derivation of the velocity, and even for the constant angular rotation, the velocity vector, the v, has in different time different direction. So you can see even I have a v here and a v here. Even the length, the magnitude of the vector is the same, it changes, there is a delta v, and if there is a delta v, the delta v over delta t is a non-null vector, there is an acceleration. If we calculate it, we can have like this, so a constant circular motion with a uniform speed, a uniform angular velocity, there will be a so-called centripetal acceleration. So this is the acceleration. We need to keep a body on a radius r with the speed v. Since v equal omega times r, you can use the formula omega square at r also. Since there is acceleration, for acceleration we need force. If this body has a mass m, the centripetal force m times v square r. So if you rotate the ball with a string, and you can even measure with a spring what is the force you need to keep this m mass body on an r circle with the velocity of v. And if it's like in this example, if this string is not strong enough at a given v, it can break, and then since there is no more centripetal force, the body will move like Newton's first axiom with a constant v in a tangential direction. Some example. Right now we skip the system and environment, we will do it later, and just go back to the circular motion, the rotation. This is what we know. And one thing, the angular alright, hard to understand from oh yes, some character missing again. So since v equal omega times r, you can rephrase the centripetal acceleration like this. And since F equal m times a, the centripetal force is mv square r or m omega square r. So if you have a ball like on this plot, this is m and this is a constant speed, and this is the axis of the rotation. The force on this string is mv square over r. So if it's not a strong enough string at a given v, it can break, and then since there is no more angular acceleration, the body will move with a constant speed in a tangential direction. So omega is a vector. Just look at this picture. So if the rotation, this is another right-hand rule, like in the like the right-hand rule for the coordinate system. If the rotation point, like in this example, with your finger you can show what is the direction of the omega. And since, so I can draw it. Oh, it's not that nice. You have a cylinder and you rotate like this. The omega will point like this, and if you speed it up, the angular acceleration increases. For example, from 1 over s to 2 1 over s, there is a so-called delta omega, and since alpha is a delta omega over delta t, in this example the alpha will also point parallel with the omega in the same direction. If you decrease the angular velocity, the alpha will be opposite to the angular velocity. Let's talk about kinetic energy of a rotating system. If you have a body with any shape that rotates over this origin or axis of the rotation, we can calculate the kinetic energy like 1 over 2 mv square. But if it's a constant angular velocity, the velocity of the body depends on the position inside this rigid body. So the v is, oops, the v is here like r1, r2, r3, omega r1, omega r2, omega r3. So the velocity depends on the position inside the body. So if you want to add the kinetic energy of these small boxes, the small elements of this rigid body, you have to sum mi vi, but we know the natural unit for rotation is the angular rotation, so you can rewrite it like sum over mi ry square, since this omega r equal v, omega times ri equal vi. So if you can do this sum, we can calculate it using anything. You can have the kinetic energy of the rotation, and this part describes the mass and also the shape of the body. Yes, this is the slide I'm talking about. And this unit, this quantity, is the moment of inertia. We can calculate the moment of inertia for simple cases, like this ring and tube and ball or one plate or something. It's easier to just memorize some formula. For example, the moment of inertia for a cylinder is 1 over 2 mr square. You can see this is only the full mass of the cylinder. Oops. The R of the cylinder, and the L, the length of the cylinder, is not in this formula, so it's independent on the length of the cylinder, the moments of inertia. Of course, in the mass, we have some information about the mass. So with the constant density, the mass depends on the L, but technically, in this moment of inertia formula, we don't have to worry about the length of the body, only the radius of the body. It's only true if we rotate the system along this long axis of the cylinder. If you rotate differently, of course the L will be in the formula. How can we use it? If you want to calculate the kinetic energy of a cylinder, for example, you have a cylinder and rotate like this, and its mass is, let's say, 10 kilogram. Its radius is 0.2 meter. Its angular velocity is let's say 1 over s, which is more like 1.5 full rotation every second, so it's not that fast rotations. The kinetic energy, the rotational kinetic energy, will be like 1 over 2 moments of inertia of this cylinder times omega square. The moment of inertia is 1 over 2 mr square. So the rotation kinetic energy is 1 over 2 mr square omega square, which is 1 over 4 times 10 times 0.2 square times 10 square. This square is 2 square, so it's 1 over 4 times 10 times 4. Yes, I see. Some part of the table is not sensitive. I have to check it. Wait. Yes, that's really hard. I try to use the lower part of the weight a bit. I think now you can see it. So the rotational kinetic energy is 1 over 2 moments of inertia times omega square, which is 1 over 2 times 1 over 2 mr square. This is the moment of inertia for rotating cylinder times omega square. If you calculate it, it's 1 over 4 times 10 times 0.2 times 10 square, and this is 2 square, which is 4, and that will be 1 over 4 times 10 times 4, which is 10, and since this is energy, this is joule. Alright, let me ask the others. For example, the drawing I did, right now, do you see it and can you understand for it how to calculate the rotational kinetic energy for a cylinder? Alright. Alright, let's do it differently. I will create new slides with only calculation. Alright, alright. We can stop this smart cup because it's pretty useless now. Let's go through the theory and then which is on the slides, and I will add few slides with this calculation, but I can finish it only for tomorrow, so we can even stop the smart cup and just go through the presentation. So what is torque? There is a so-called vectorial multiplication, and the torque is nothing else just the force and R cross force. If yes, I used to draw it. All right, let's stop it now. I will create new slides because I usually draw everything on the table like in the seminars, and since you can't see it from the smart cup, let's stop it now, and tomorrow I will add these slides and you can understand it better. So sorry and thanks for your patience. Let's meet tomorrow and continue with only the slides, but for that I have to do that. We can stop now if you don't mind, because it's worthless to continue like this. It's okay. I just tried this table. If it doesn't work, I have to do something. Thanks, and see you tomorrow.